In this biomechanics problem, we're trying to find how much force the muscle or the tendon has to exert to keep this ankle in equilibrium under these conditions. So, what we're trying to find is that force F sub t. And what we're given in this case is that the problem is in equilibrium in that the sum of moments around point A is going to be 0. So in our diagram, we have our point A, which I'm going to designate as the origin of our system. And what we know is what the normal force is acting on the toes. So this normal force, we could get if the person was standing on a force plate or standing on a scale, we'd be able to measure what that force was acting up. So that normal force is 400 newtons. And that's acting 100 millimeters from, in this case, what I designate as the y-axis. Now also acting is the force of the tendon pulling up, which we're told is 5 degrees from the vertical. And again, this is force F sub t. So what we're looking for, this is 65 millimeters. So what we're trying to find is what is the force in that tendon that's keeping this in equilibrium. So again, this is our diagram. So as far as our equations go, well, we can use our information from the given. When we add up all of the moments caused by forces around A, we know it's going to add up to 0 because they told us this is an equilibrium. So now we have to look at what forces are causing moments around point A. So first thing we can see is that around point A here, we are going to have a moment caused by that normal force of 400 newtons. So it's going to be, we're using that moment is force times perpendicular distance. This 400 Newton force is already vertical, so it's going to have a magnitude of 400 newtons. And the perpendicular distance from A, so remember we can move this along its line of action, and we want to see what is the distance between point A and its line of action, that perpendicular distance here. So this distance we're already given is going to be 100 millimeters. So notice I'm keeping everything here measured in millimeters. I'm not converting to meters. As long as I have consistent units, this is okay to do. So let me actually rewrite this as 400 newtons times 100 millimeters. Now, what we have to decide is this normal force causing a positive or a negative moment around point A. So if we hold our pencil here, we push in this direction of the 400 newtons, it's going to be causing a counterclockwise moment around A or a counterclockwise spin around A. So this is going to be a positive quantity. Right? And this is already vertical, so we're done with the moment caused by the 400 Newton force. Now we want to pay attention to F sub t. Now F sub t is 5 degrees from the vertical here. So what we want to do is, as we saw before, we can rewrite this as a vertical component and a horizontal component. So the vertical component here, we'll break it down, is going to be Ft, which again is right now unknown, and the part that's vertical is adjacent to that 5 degrees. So that's going to be Ft cosine 5 degrees. And then we want to look at what's that perpendicular distance between the vertical component and A. So it's going to be this distance here, which we already know is 65 millimeters. So this is going to be measured in newtons times 65 millimeters. If we now want to know is it positive or negative, hold down at A. If we push in that direction of that vertical component, the whole system would want to spin clockwise. So this is going to be negative. Now we want to look at the horizontal component of Ft. We see, since it's acting here and we're drawing it to the right, that line of action intersects point A. So as far as the moments caused by the horizontal component of Ft, that is going to be 0 because its distance, its perpendicular distance to A, is going to be 0. So this is our complete equation for the sum of moments around A. So we have one equation, and the only thing we don't know is this F sub t. So we can solve this for F sub t. So the force in the tendon that will make it so that the moment around A is 0, we're going to get a force of 618 newtons.